X inactivation is a phenomenon that you only see in females, and in humans, X inactivation occurs because females have two X chromosomes, whereas males only have one. So, just to review, a female human has 22 pairs of autosomes, which are the regular chromosomes 1 through 22. And then she has an X chromosome and an X chromosome. So 22 pairs, which is 44, and this is number 45, and this is number 46. Okay, so 22 pairs of autosomes and two X's. Whereas a male has 22 pairs of autosomes. Oops. Start over. And an X and a Y. All right, so you can see from this that the female has two X's, the male only has one. So in a way, and the male obviously can survive with just one X. You don't have to have two X's to survive. You can survive with one. 50% of the world does fine with one X. That's all the males. So in a way, the female with her two X's here, she kind of has one extra than what's really needed. So we have a phenomenon that occurs called X inactivation in a human female cells. So if you imagine a human female cell, every cell of her body has these 22 pairs of autosomes plus the two X chromosomes. One of the X's in every cell is kind of condensed up, wrapped up, and kind of stashed away on the edge of the nucleus and not used. Only one X is active at any one time. All the other chromosomes, both of them are used. Both the number ones, both the number twos, both the number threes, both the number fours, all the way up to number 22, both the number 22s are used. But when it gets to the sex chromosome pair, only one of them is needed. And so the other one is kind of stashed away. It's like putting your Christmas decorations in a box and putting it in the garage and forgetting about it. This other X, the second X, it's not extra, but the second X is highly condensed. The DNA is wrapped up around histones and crunched together and just stashed on the edge of the nucleus. And you can see in this diagram here, there's this like darker dot on the edge of the nucleus. That is the second X chromosome that is all condensed and kind of put away. I say put away, but just kind of stashed off to the side. It's called a bar body. All right, so males don't have bar bodies. They don't stash away an X because they've only got one and they need it. So they can't not use it. They have to use the one they have. So this does not happen in males. Now, the reason why it's significant is that the X chromosome doesn't just, it carries lots of different genes, not just genes that are for sex determination or reproduction. There is many, many, many genes on the X chromosome, genes that have to do with eye development, genes that have to do with brain development, genes that have to do with blood clotting. I mean, there's just random genes that have nothing to do with femaleness or maleness. They're just to do with being a surviving human that are on the X chromosome. And so because you get as a female one of your X's from your mom and one of your X's from your dad, they're not identical. Your two X's are not the same if you're a female. One came from your mom's lineage and one came from your dad's lineage. And if there's an error or a mistake on a gene on one of those X's, you might get a good version of the gene from your mom, but a version of the gene with an error from your dad, or vice versa. Now, in a cell, the cell chooses at random which X it stashes away. It might stash away your mom's X, or it might stash away the X you got from your dad. It just happens at random in every single cell. So if we look in this diagram here, this first cell, this cell has chosen to stash away the X that came from this individual's dad. That's why it's color-coded blue. In this cell, the cell decided to stash away the X that came from the individual's mom. It just is like a coin flip, which one gets stashed away. Now, the situation is that they're describing here is a condition where there's a gene carried on the X chromosome that is responsible for making sweat glands function. So this is sweat glands in your skin, has nothing to do with sex or reproduction, just making sweat glands that everybody needs. Now, in this situation, the X chromosome has a version of the sweat gland making gene that is not working. And the dad's version of the X chromosome has a version of the sweat gland that is working. But unfortunately, this cell has chosen to put away the version of the gene that works, and is using the version of the gene that doesn't work. So every cell in the skin that is using this X is not going to be able to make sweat glands. Every part of the skin that is using this X is going to be able to make sweat glands. So this female has patchy skin in terms of sweat gland production. Some of her areas of skin can sweat, and some of her areas of skin cannot sweat, depending on which X chromosome those cells are using and which one they've put away. So it's a very weird scenario. Only happens in females. Men do not get this condition. They can either sweat everywhere or they can't sweat everywhere, depending on whether they got an X that has the gene for sweat glands or an X that has a messed up gene for sweat glands. And they've only got one X, so they've got to use the one they have. But because females can randomly use one X or the other, the two they have, they'll have patches of skin that potentially can sweat and patches of skin that potentially can't sweat. Now, most females, both our X chromosomes have a good version of that sweat gland gene. So it doesn't matter which X we're using, it's all going to be functional. So you can sweat everywhere. But there are certain people who inherit a bad X, or not a bad X, inherit an X that has a malfunctioning sweat gland gene, and any cell that's using that X is going to not be able to make sweat glands.